University of Western Macedonia, empowering your future.
Well, let us begin. First of all, let me say that the meeting is recorded and it will be uploaded to the website of our university. And let me introduce Professor Michalis Matthaiou. Professor Michalis Matthaiou was born in Thessaloniki, Greece in 1981. He is a professor of communication engineering and signal processing and deputy director of the Center for Wireless Innovation at Queen's University, Belfast in UK. His research interests span signal processing for wireless communication beyond massive MIMO, intelligent reflection surfaces, millimeter wave terahertz system, and deep learning for communication. And he has published more than 280 papers on these topics. And he has received several prizes, like the Leonardo G. Abraham Prize in 2017, the Euroship Early Career Award, and the Royal Academy of Engineering. Moreover, he is the holder of the ERC Consolidation Grant Beatrix that focuses on the interface between information and electromagnetic theory. Michalis Matthaiou is an editor-in-chief of Elsevier Physical Communication, a senior editor of IEEE Wireless Communication Letter, and IEEE Signal Processing Magazine, and an associate editor for IEEE Transactional Communication. Finally, Michalis is a IEEE Fellow. Michalis, the floor is yours.
Hey, thanks, Alex, for this wonderful introduction. And thanks everyone for joining the meeting, taking the time of your work to attend the meeting from different parts of the world. So today we'll be talking about a technology that my group has kind of done a lot of research on, and that is cell-free massive MIMO. So we started looking in cell-free massive MIMO in very early days. That would be 2017, 2018. And now, of course, research on cell-free massive MIMO has taken off, literally. So there are many different groups around the world are working on cell-free massive MIMO at the moment. So what I would like to do today is I'd like to articulate where we are with the cell-free massive MIMO research and just present a snapshot of our most recent contributions in this space. All right. So let me start my presentation by sharing the screen. All right. So hopefully you can all see my screen. So I take silence as a yes. So this is a joint work with two of my postdocs, Dr. Mohammadi and Dr. Mobini, and Dr. N. Go, who is an associate professor here at Queen's University, Belfast. Before I start with the technical part, I would like to give a brief introduction of the university I work for and the group I'm co-leading. So Queen's University, Belfast was how can I minimize this? So was established in 1845 by Queen Victoria and is the 9th oldest university in the UK. So as you probably know, UK consists of 4 countries. You've got Scotland, England, Wales, and Northern Ireland. So Belfast is the capital of Northern Ireland with a total population of 500,000. So the university is a major component of the city. And at the moment, is home to pretty much 25,000 students around the world, and with a total revenue of I think the university contribution to the local economy is in excess of 3 billion per year. All right, and historically, Queen's is top on the investment So, and commercialization activities in the UK, and I think it's tied with the University of Oxford, if I remember correctly. So now, regarding our CWI, the Center for Wireless Innovation, so it was formed in 2016 following the consolidation of two groups that were sharing facilities, but they were not, from an administration point of view, in the same group. That would be high frequency electronics and wireless communications. So wireless comms and high frequency electronics in Belfast has a history that goes back in the mid-70s, right? And at the moment, the CWI is the UK's largest research development and exploitation based in physical air wireless. We are in excess of 70 people and we are growing continuously. We are home to 3 IEEE fellows, and we are consistently within the top 75 of groups in telecoms engineering according to the prestigious Shanghai rankings. All right. So the research we do is quite diverse. So it covers different areas from fundamental COPS modeling, that would be my area, all the way up to antenna design, imaging, sensing, biomedical implants. And this is done in a way that integrates academics with engineers. So at Queen's, we have a unique model where we are very fond of translating academic research into commercial products, right? So, and I believe we have been quite successful in this aspect over the past 10, 15 years. Now, these are some of our collaborators. Maybe some of the logos are familiar. So we've been working with the likes of Ericsson, Samsung, Nokia, Bell Labs. Ofcom is the UK Spectrum Regulatory Authority, so it's equivalent to the American FCC. And DSTL is the research arm of the Ministry of Defense, right? So we have also strong bonds, historical bonds with European Space Agency, and many of my colleagues are building antennas, radio-directive antenna arrays, frequency selective surfaces for ESA over the past 20 years. Now, right. So now let me start becoming a little bit more technical. So let's talk about the basics of cell-free. Now, you see here two snapshots of base stations, right? On the left, you see a conventional macrocellular base station, right? So typically deployed on the tops of hills, and here you would see some base station antenna array panels that are deployed on rooftops. Now, this kind of architectures have been working extremely well for the past 50 years, ever since the concept of cellular communications was first introduced in the mid-70s. Now, the problem is that the base stations are typically quite far away from the users, right? So this is causing large signal strength variations. And in a sense, it means that some users, if they are lucky, they may get extremely high quality of service, whereas other users may get nothing, right? And in terms of fairness, this is not nice, right? Just imagine some users having an extremely high, video call quality, and other users couldn't get access even to basic cellular services, right? So this is what has motivated the development of cell-free massive MIMO. Now, we are moving away from the conventional cellular structure where we would have a base station typically at the center of a hexagonal cell serving the users in its cell, and we move away from that into something more, I would say, less regulated, right? So in a sense here, sorry? Okay, there's some background noise anyways. So here there are no cells, right? There are no cell boundaries. Instead, we have access points, as we call now the base stations, we call them access points, that are geographically much closer to the users and can perform coherent precoding and decoding, and therefore we can avail of macro diversity gains, right? Now, today I will be talking about some of the applications of cell-free massive MIMO that my team has looked into. And of course, that list is non-exhaustive. Right now, cell-free massive MIMO, as I said at the very beginning, can be has literally taken off, so they can be applied to different kind of application scenarios, right? Now, my interaction with cell-free massive MIMO goes back to 2017, whenever the first paper came out by my colleague here, Eric Larsson and Tom Marzetta. The first paper we published on cell-free massive MIMO was in 2018, in March 2018, and until today is the most highly cited paper in the history of IEEE transactions on green communications and networking. In that paper, we saw how we can optimize the energy efficiency of cell-free massive MIMO, all right? And since then, my group has published in excess of 60 scientific papers on cell-free massive MIMO. So we are talking, what I'm trying to say is that cell-free massive MIMO is a core expertise of my research group here at Queen's University, Belfast. Now, the first application I would like to talk about is how we can combine cell-free massive MIMO with an emerging modulation protocol called OTFS, orthogonal time frequency space modulation. Now, I'm not sure how familiar you are with OTFS. That's a technique proposed in 2017 by Hadani and the co-authors. And the main idea is, the main motivation actually was the shortcomings of OFDM when we are in high mobility, when we deal with high mobility scenarios. In this case, the Doppler spread becomes excessively high, and this breaks the carrier orthogonality between OFDM symbols. And if that orthogonality is broken, then the whole system performance is substantially compromised. Now, OTFS is precisely addressing this challenge. It is Doppler resilient, so this means that it can perform extremely well in high mobility, double dispersive channels. Now, this is a snapshot of how OTFS operates. OTFS operates in the delayed Doppler domain instead of the time frequency domain as OFDM. So this is the time frequency domain, all right? And this is the delayed Doppler domain. So we have a high mobility scenario here that it will take two snapshots at time t0 and time t0 plus delta, right? So what we have here on the left-hand side is the power delay, the 2T power delay profile in the delayed Doppler domain. As you can see, if you compare these two graphs, you would see that the number of paths is relatively small, right? We only have 4 non-negligible paths. And the power of these paths seems to be relatively unaffected when we move from this scenario to this one. Now, on the right-hand side, we have the conventional time frequency representation. Here, the channel has many more components, non-negligible components. And most importantly, if you compare this subfigure with this one, you would see that the power of some paths is going up, the power of other paths is going down. So it's hard to, this scenario is definitely not static, whereas this one is relatively static and sparse. Okay, so this sparse and static behavior in the delayed Doppler domain is what makes OTFS quite attractive for high mobility scenarios. All right, so I'm going to skip this one because I don't want to become too technical right now on OTFS. There are lots of papers, lots of overview articles that describe how OTFS can be implemented using the symplectic Fourier transformation. Now, what we have tried to do in this paper is to bridge a gap that exists in the literature. So most works on combining massive MIMO with OTFS have been focused on colocated massive MIMO. So we have an extremely high antenna, extremely large antenna array, massive MIMO antenna array, trying to serve users using OTFS protocol. There have been lots of works on, as I said, not lots, but there have been works on this topic. Here, we have moved away from the collocated massive MIMO case because results derived for collocated massive MIMO cannot be directly extrapolated to cell-free. All right, there's a different story there because we have distributed access points and a large number of access points. And we have also tried to derive in closed form analytical expressions for the spectral efficiency. And we have also looked into asymptotic scenarios. And we have published 2 papers in last year, November 2022, and another one follow-up in June 2023. So we have tried to do a performance analysis, a channel estimation protocol design, and also a resource allocation. And then we compare what we have against the state of the art. Now, as I said, we have the closed form expressions. We consider a new MMSC successive interference cancellation detector, which does not require any codebook design. And we also look into the power scaling laws. What happens when the number of access points grows large? How much we can cut back the transmit power, and then things like that, and see what happens in the asymptotic limit. Now, we consider different benchmarks. We consider OFDM with block type pilot pattern. We also consider OTFS with uniform power allocation, and then we have different processing schemes and different detectors. This is taken from this reference, and this is the proposed one, MMSC serial interference cancellation. This one is a lower bound of this one, but with much less complexity. All right. So these are some graphs here, as you can see. So EP here stands for embedded pilot, where we insert pilots to avoid interference between pilots and symbol, and SP stands for superimposed pilots, where we superimpose a data symbol onto a pilot symbol. Now, as you can see here, the LMMSC, all right, with EP and SP offers 2.6 and 4.3 fold higher spectral efficiency compared to maximum ratio, which is another benchmark we consider. Now, here we see that as you increase the number of access points, the average downlink spectral efficiency kind of saturates. Okay, this was shown also analytically. And we also see that the performance of MMSC, SIC, and local low complexity detector, LCD, are very close to each other. But remember, MMSC, CIC comes with much lower complexity. Now, some more graphs here comparing the different detectors. As you can see, these two are very close to each other with complexity that's significantly reduced. Whereas here we compare the effect of power allocation. Okay, so optimum means optimum power allocation, and uniform means uniform power allocation. So we see here a substantial increase in the 95% likely rate. Okay, so far so good. We have a full protocol, analysis protocol, and we believe that we advocated nicely how cell-free can be combined with OTFS. Now, next topic is how we can combine cell-free with full duplex, right? But we don't do that in the compression.
I have a question. So when you say MMS SIC, I mean, do you follow any ordered, like there are various variants of SIC, like either you can, I mean, I'm just talking from the singular values perspective. Do you do any ordering there, or what kind of SIC do you use actually?
Yeah, so we order the eigenvalues. Yeah.
Okay. But there are. I mean, did you try looking for other SICs, or it's the eigenvalue? I mean, ordered SIC is the best.
No, I'm not saying it's the best. It's the, you could do something different, right? You could go for another alternative, but what we did here, this was a follow-up of this paper, right? So this was a letter. Okay, so the contribution was not mainly on the MMSC CIC, but instead on the power allocation. So we consider an ordering of eigenvalues, and then we develop an algorithm for allocating power to the users in order to maximize the energy, the spectral efficiency, right? So that was the major contribution, if that makes sense.
I'm sorry, like, what is the amount of interference? Like, how is it, like, how many users are interfering one particular design? Sorry, maybe I'm asking for more details, but.
Sorry, I don't have the numbers of the number. I don't have the number of users in front of me, right? But normally in our simulation, consider between 10 and 20.
10 or 20 interfares.
Well, 10 to 20 user equipments. So if you look at one user, that would be either between 9 and 19 interferers.
Okay.
All right.
Yeah. Great.
Okay.
Thanks.
No problem. Now, so the second idea we looked into was how we can combine cell-free with full duplex. But as I was saying before, we're not trying to do the conventional full duplex, all right? And I will explain very shortly why we didn't go for the conventional full duplex. So this is just an overview slide where we compare half duplex versus full duplex, all right? So we have a half duplex topology here where we spend some of the resources, for downlink data transmission and other orthogonal resources for uplink data transmission. Now, this scheme is not ideal when latency is a concern and when we want to prioritize uplink or downlink users. Now, an more sophisticated version of half duplex would be full duplex, where we transmit the downlink and uplink in the same time frequency resources. Ideally, that's a brilliant idea because it would double the spectral efficiency, but there are some fundamental challenges here. The first one is that you need a robust transceiver that can mitigate the self-interference. That is the interference arriving to the receiver chain of the relay device from the transmitter. And you also have additional sources of interference, the likes of cross-link interference, where the transmission of one base station interferes with another base station. All right. So let's see whether these challenges can be properly addressed. Here, the answer to this question is yes. And we saw this using a new architecture that we called Network Assisted Full Duplex, NAFD. Here, we use only half duplex access points to support uplink and downlink transmission. Okay, at the same time. Here, we have no self-interference, and the implementation complexity, power consumption, and the access point is much lower. Whereas if someone goes for both full duplex and half duplex access points, we would have both self-interference and cross-link interference, and we need to manage this excessive amount of interference, right? So in this paper, we design a full protocol, mainly focused on optimization of the spectral efficiency and energy efficiency that relies on statistical CSI. That is very important because statistical CSI remains static for lots of coherence intervals, and therefore it's much more scalable to implement algorithms on statistical CSI basis rather than on instantaneous CSI basis. All right. We also did an access point mode assignment, and we'll see what we get. So the results of this paper were published a few months ago in IEEE Journal Selected Area and Communications. And as you can see here, these are our design parameters. We want to switch between uplink reception or downlink transmission for the access point. We implement a power control, and we also select the large scale fading decoding weights based on our proposed algorithm. And our design objectives was to enhance the spectral efficiency and improve the energy efficiency. the findings of this work are quite remarkable. First of all, we saw that cross-link interference still exists, but is much more manageable. We also observed that the spectral efficiency is significantly enhanced, mainly due to the mode assignment and power control, and energy efficiency is also significantly improved because there are no power-hungry circuits for self-interference cancellation, as in conventional full duplex. All right. So these are, okay, I'm gonna skip this. Now we are comparing the proposed network assisted full duplex, the RNFID, the first one here, okay, and with the greedy NFID, okay, where we have fixed power control coefficients, with a conventional half duplex with a conventional full duplex. So let's see what we get. Let's first look at the average sum spectral efficiency. As you can see, the proposed scheme is the red curve, right? It's the top one. That's very good news. Full duplex comes second, and then you have the other schemes, all right? The GNFID, the greedy, and the random NFID, all right, which is greedy and random, which do not perform so well, and half duplex is somewhere here. Now, what I would like to point out when I move from the spectral efficiency to the energy efficiency is the substantial reduction of full duplex. See, full duplex here is second in performance. Here is one from the end. Why is that? Because when you calculate the energy efficiency, the power consumption to perform self-interference cancellation kills all your spectral efficiency gains. Remember that the energy efficiency is the ratio of the spectral efficiency over the total power consumption. So if you increase the denominator dramatically, then your energy efficiency will eventually come down. All right. So that's the problem with full duplex. Again, the proposed scheme performs extremely well and outperforms all other benchmarks. Some more plots here showing the spectral efficiency versus number of antennas and the energy efficiency. All right, I'm gonna skip this and move on to the third topic, how we can combine cell-free massive MIMO with SWIFT, simultaneous wireless and information power transfer. This has been another hot topic for the past 7-8 years. So what we have tried to do here is we noticed that conventional cellular networks with a massive antenna array in the center of a cell may run into blockage effect, where a big building is blocking the communication between the base station and the user, but not only the communication, also the energy transfer. Instead, if we spread access points within a geographic area, we can avail of high microdiversity gain and low path loss, and therefore transmission of information and energy becomes much more robust. Okay, so there have been works in this space, all right, but the problem is that they do not consider the resource allocation problem, right? So they typically consider orthogonal transmission through TDD and orthogonal transmission between the energy transfer and wireless transfer, okay, wireless information transfer. Now, they also don't consider the transmit power requirements, and therefore we believe that our contribution is bridging this gap. So what we presented actually last week in Kuala Lumpur during GlobeCom is this system model, all right, where we perform SWIFT using cell-free massive MIMO, and we are trying to enhance not only the spectral efficiency of the information users, but also the harvested energy of the energy users, all right? So, and then we have the design criteria, as I said, is to maximize the total harvested energy and improve the energy efficiency, all right? So this is the main objective here. Now, these are the contributions. I'm going to skip this. And these are some of the benchmarks, all right? So as you can see here, we have 3 benchmarks. We have the first one is random access point operation without power control. Here is random access point with power control. And here is a conventional sweep with orthogonal transmission, all right? And let's see now how these can operate against each other. So here we are plotting the sum harvested energy power. The proposed scheme is the blue curve. Compared with the 3 benchmarks, we see a substantial improvement in the harvested power, okay? And here we plot the sum harvested power against the number of antennas per access points. Here we see a little bit strange behavior. We see that the harvested power first goes up, reaches an optimal point, and then starts going down. Well, this is not surprising, because if we increase the number of access point, if we increase the number of antennas per access point, then it means we have more degrees of freedom for energy harvesting at the energy users. Okay, but at the same time, we keep here the number of, so we have to reduce the number of access points in order for the product of antennas times access points to be the same. So less access points means longer distance from the access points to the energy users. So the effect of the path loss would effectively undermine the extra degrees of freedom. So that's why we see that first, then harvested energy goes up, reaches an optimal point, and then starts going down. Here in this regime, the effects of path loss is killing the degrees of freedom by the extra antennas per access point. Okay. Now, another thing that I would like to talk about today is how we can combine massive MIMO with RIS in order to perform sweep. Now, this is not a cell-free idea; it's a conventional massive MIMO, but I believe falls under the general umbrella of massive antenna technologies. All right. Now, here we have a base station. All right, who would like to transmit information and power to some users. The problem is that those users are behind a big building that is blocking the transmission. Now, by leveraging the concept of RIS, we can create an additional path that would serve those users. Okay. Now, in this paper, we consider imperfect channel state deformation. We also consider low complexity nillinear precoding designs, because we know after so many years of research in massive MIMO that things like MRT, zero forcing, or the new variants, protective zero forcing or full zero forcing, can perform extremely well, and we don't have to do any super sophisticated nonlinear techniques like maximum likelihood. Okay, so we presented this work in June 2023 during ICC. Okay, so we proposed a zero forcing and protective MRT, all right, in order to simultaneously transmit information and energy, and moreover manage the inter-user interference. And we also designed a 2-time scale scheme, all right, that is based on long-term statistical CSI. This is again very important. I would like to articulate this today for people who just started looking into these problems. Long-term statistical CSI is a very important asset that can open up many opportunities in your research, because you can, instead of working with instantaneous channels that change very frequently, you can work with things like the covariance of them, second-order statistics. And the good news is that we know mathematically, many techniques to work with this quantity, second-order statistics. Now, this curve shows different code books. We have a DFT and random, okay, and we are plotting the average per user harvested power here, okay, against the number of antennas. And here, a similar graph where we change the number of information users and energy users. Okay, so we see that here this n here is the number of RIS elements. We see that by increasing the number of RIS elements, the performance between the Rician and the Rayleigh cases, okay, is reduced, okay, because more scattered waves can be steered towards the energy users. Here we see that by increasing the number of energy users, the minimum per energy user power is decreased. However, the total amount of harvested power is increased, okay? Now, the last thing I would like to talk about today is another paper that we presented last week in Globecom, is how you can combine cell-free with Isaac, okay? Now, Isaac is another hot topic that that many groups are working on at the moment. And there have been indeed works on how to combine massive MIMO with Isaac. All right. So my good friends here, Fan Liu, Chris Masouros, and others have published this famous paper in 2018. And here we are trying to do something different. We can try to avail of a cell-free infrastructure to serve both sensing and communications users, all right? And we do that by developing an algorithm that makes sure that we maximize the minimum spectral efficiency of the communication users by satisfying specific sensing requirements given by variable kappa, all right? So these are some of the graphs. So this is the CDF of the spectral efficiency, all right? And this straight line represents the 95% likely spectral efficiency. And as you can see, we have three graphs, okay? So GAP stands for gritty access point mode selection, and OPC stands for optimal power control. Okay, so this one is the optimal one, all right? And NPC stands for no power control, and RAP stands for random access point mode selection. So as you can see, if you compare the black curve with the blue curve, you see a significant increase. But if you compare now the black curve with the red curve, the increase is more than huge. Okay, it's really massive. And now another observation is that by increasing when kappa decreases from 15 to 10, okay, this is 15, this is 10, the 95% likely spectral efficiency increases. And this is because a greater number of access points are assigned for downlink communication. And this is also shown here. The proposed scheme, okay, the black curve, meets not only the sensor requirements, but also delivers extremely high spectral efficiency. So to conclude this, my presentation today, I believe that cell-free massive MIMO is not just another technology, it's the right way to do distributed MIMO or network MIMO. And some people think that cell-free massive MIMO competes with conventional massive MIMO. The answer is that cell-free massive MIMO is an evolution of colocated massive MIMO, right? Personally, I've been working on massive MIMO for, 15 years now. And cell-free massive MIMO was, again, I never thought that it's competing massive MIMO. It's just, as I said, the natural evolution. Now, it's also cell-free massive MIMO is a research gold mine because you can combine different tools, techniques you know from information theory, signal processing, whether that would be distributed or centralized, optimization, resource allocation, cross-layer design. You could either, combine it with optical communications to develop a reliable backhaul link. And on top of that, you can integrate cell-free into other existing or emerging technologies, the likes of RIS, XLR scale MIMO, Isaac. sweep, terahertz, sensor networks. So there are lots of opportunities there. So, I just strongly recommend to look into cell-free and see what opportunities are available. And with that, I would like to conclude my talk. Thanks for staying with me and not falling asleep. Hopefully not. All right. Thank you very much. Happy to take questions.
Thank you very much, Michalis. Let's open the floor for questions. So if someone have a question, please raise your hand. Okay, so I have some questions, to be honest. And
Okay.
let me open the floor with questions with my question. First of all, as the number of elements increases in an antenna and we are going to massive MIMO, the near-field transmission range, the near-field distance also increases. Am I right in this?
Yes. Yes.
So let me go to, is this an opportunity? We know that we have a better power transmission for energy harvesting in the near field than in the far field. Is this a topic that is this a true assumption? So is it something that we are exploiting? For example, we have sweep for near field, or we can also have sweep in far field.
This is a very good question, actually. You are indeed right that as we increase the number of antennas, the Fresnel distance or the near field zone also increases, right? So there are indeed many opportunities to do near field energy transfer. One idea that was proposed by some researchers in MIT in 2008 was called witricity. So in a sense, they did that with using magnetic coils, but and they managed to achieve the resonant frequency in order to have maximum energy transfer. Don't forget that the resonant frequency, the magnetic and electric field are the same, are equal, and in that case, the flow of energy transfer is maximized. Okay. The problem with that, if you see the actual demonstration, it was like two huge magnetic coils that is hard to be deployed in real life. All right. Now with RIS and with reconfigurable antennas, there might be opportunities to adjust the resonant frequency in a much more sophisticated way rather than going for a super bulky solution. So the answer to your question is yes. Sweep to near field is an extremely timely topic.
Okay, and another question. As the number of antenna elements increases, we have two ways to go forward, or maybe three ways. One is the analog beamforming, the other is the digital beamforming on the other hand, and also you have the middle one, that's hybrid beamforming, if I can put it in an axis. In analog beam, you can use analog beamforming in millimeter wave and terahertz in order to increase your transmission distance. While digital beamforming, you increase your diversity in the system. However, their main difference, if I remember correctly, is the energy consumption. Because the energy consumption in the second case, it's much larger than in the first one. So what do you believe is the way forward, and what are the limits of the systems? For example, are we expecting next year to have a system with 1,024 elements, an antenna that has 100 RF chains behind it, or something else? Because I remember your paper with Marzetta, sorry, that you said that you write somewhere there that you need 100 elements per user in order to call a system a massive MIMO system, if I remember correctly the analogy. Please correct me if I'm wrong.
Yeah, well, maybe I was not the author of that paper, but I know what you're talking about.
Oh, sorry.
It's all right. It's okay. Understand the question. So now, analog beamforming, okay, it's a little bit, to me, it was always from the get-go, was a little bit odd because in the area of digitization, going back to the analog domain sound a little bit awkward, okay? I understand why people want to invested a lot in that because it's the complexity issue and so on. Now, to me, at the end of the day, is a trade-off between complexity performance and how many antennas do you really need. All right. There are scenarios that you will need 64 antennas, and that will do the job. You can then, in this case, you can deploy easily a 64 full digital architecture. That's no problem. Now, if you want to go to the hundreds or thousands, then we need to think of alternatives. Okay, and particularly at extremely high frequencies, the likes of terahertz. How you cannot have a 1024 full digital architecture operating at 300 gigahertz. That's a no-brainer. Okay. Now, in this case, as I said, maybe you need to sacrifice the performance for the sake of complexity.
I totally understand. There's two questions in the chat. Let me read it for you. Okay. Is there any part that you think we can use AI cell-free MIMO? It's the first.
Well, absolutely, yes. The resource allocation problem is highly complicated, and you reach a point where the conventional optimization techniques just don't work or break down. We have a number of papers on how you can develop deep neural networks for resource allocation in cell-free, how you allocate power, okay, how you select access points to perform a specific task. That can be downlink transmission, that can be energy transmission, all right? So there is plenty of room to apply AI in cell-free massive MIMO problems.
There is another question, maybe it was to my chat. Could you please elaborate further on the advantages of long-term statistical CSI?
Yeah, all right. So from a practical point of view, the answer to this question has two pillars. The first one is the practical point of view, and the other one is the mathematical point of view. So the practical point of view is that statistical CSI changes over a much longer coherence interval. All right. In practice, that would be 40 coherence intervals. So in a sense means you don't have to frequently sample the channel every 1 millisecond, right? Or every 1 kilohertz. So you put a big chunk of, resource blocks together, and then you average over it and you have the statistical CSI. When you work with instantaneous CSI, you have to sample the channel in every coherence interval. All right. And that is going to kill the complexity and the resources. Now, from a mathematical point of view, if you work with statistical CSI, effectively you are working because everyone, in comms is working with Gaussian channels, or the majority of the people. You're effectively working with second-order statistics of Gaussian vectors, covariance matrices, and so on, and then you have whatever the channel is, Rayleigh, Rishan, you may have zero mean, non-zero mean. And the good thing is that mathematically, we know extremely well how to work with these covariance matrices, all right, for transceiver design, resource allocation, and so on. We know the properties, we know the eigenvalues, we know the asymptotic behavior, and that's why statistical CSI helps a lot.
Thank you very much, Michalis. Is there any other question? Okay, so once again, thank you very much for this interesting presentation and for accepting our invitation.
That was a pleasure. Thank you very much. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you. Bye.
Bye. Bye, everyone. Thank you. Thank you.
Thank you.
Thanks.
Mm.